IMPA, afortunadamente para nós. E hoje ele vai nos falar de Conformally flat hypersurface in R4 with three distinct principal curvatures. Obrigado.
Thank you, Espinar, for the introduction. And thanks also for the organizer for the opportunity to give this talk. Well, most of the new results I would like to report on this talk is based on a work in progress, actually, with Carlos Gonçalves. And, well, the general problem behind what I would like to discuss is the following: is for which immersed hypersurfaces of dimension at least 3 is the underlying manifold conformally flat with the induced metric. Well, notice that we are excluding the surface case from this problem, of course, because conformal flatness imposes no restrictions on a surface, just because the well-known fact that on any two-dimensional Riemannian manifold, one has isothermal coordinates around any point. Well, we call that a Riemannian manifold is conformally flat if each point of it has an open neighborhood which is conformal to an open subset of Euclidean space. Well, actually, I will also be interested in examples with constant mean curvature or minimal, and in understanding how many of such hypersurfaces there exist. Well, as we will see during the talk, the most interesting case with regard to this problem is the case n equal to 3. But I will start by reviewing what happens in higher dimensions. If n is greater than or equal to 4, one has this classical result by Cartan, which says that if we have a hypersurface in a space form with dimension at least 4, then it's conformally flat if and only if the hypersurface admits a principal curvature with multiplicity at least n minus 1. So a conformally flat hypersurface in Euclidean space, for instance, is just an envelope of a one-parameter family of hyperspheres. And it can be explicitly parametrized by a curve and a function on this curve by the so-called conformal Gauss parametrization. So in regard to the general problem I started with, there is not so much to say else in the case in which n is at least 4. And if one adds an assumption like having constant mean curvature or being minimal, one can use this result by Manfredo and Marcos, which says that if you have a hypersurface with only 2 distinct principal curvatures, one of which with multiplicity n minus 1 and the other one simple, and if those principal curvatures satisfy functional relation, then it must be an open subset of a rotation hypersurface. And for instance, if the hypersurface has constant mean curvature, you can explicitly describe the profile curve in terms of solutions of a certain ODE. In particular, if you consider the minimal case, then you have this result which extends a previous one due to Blair in the Euclidean case, which says that a minimal conformally hypersurface with dimension at least 4 must be an open subset of a generalized catenoid. It means that the hypersurface has a profile curve which in dimension 2 coincides with the usual catenary. So from now on, I will focus on the most interesting case of dimension 3. Cartan himself already realized that there exist examples of conformally flat hypersurfaces of dimension 3 in R4, which have 3 distinct principal curvatures. And one can construct explicit examples as follows. These are called the conformal product hypersurfaces. For instance, one has cylinders over surfaces in R3 with constant Gauss curvature. You start with a product of a 2-dimensional Riemannian manifold with constant curvature C with R, and just take the cylinder over the surface, which is conformally flat because a product like this is always conformally flat. Another example is a cone over a surface in the 3-sphere with constant Gauss curvature. Intrinsically, the hypersurface is also a product like that. And now you just immerse the surface in R3 and parameterize the 1-dimensional hyperbolic space. And then you compose with this conformal diffeomorphism of S3 times H1 into R4. Well, the image omits a point, and this is a conformal diffeomorphism with just spherical coordinates reparametrized. And then you get a conformal immersion of this Riemannian product into R4, whose image is a cone over a surface in R3. In particular, if you take the cone over a Clifford torus, you get a minimal conformally flat hypersurface, which has 3 distinct principal curvatures, one of which is 0. As a further example of a conformal product hypersurface, you can take a rotation hypersurface over a, rotation hypersurface over a surface in H3 with constant Gauss curvature. You construct it like that. You consider a half space in R3 and look at it as the half space model of hyperbolic space. And then you take a surface in this half space which has constant Gauss curvature with the induced metric from the hyperbolic metric. And then you just rotate this surface. You get a hypersurface in R4 which intrinsically is again conformal to a Riemannian product like that. And you compose this product immersion with this new conformal diffeomorphism, which now its image omits this asymptotic boundary of hyperbolic space. It's a conformal diffeomorphism. And the image of this immersion is a rotation hypersurface over this surface you started with. So these are simple examples of conformally flat hypersurfaces in R4 which have 3 distinct principal curvatures. And one can characterize those examples by the property that one of the families of curvature lines are made up of segments of circles or straight lines. This was observed in a result in a paper with Marcos and Luis. Those conformal product hypersurfaces can be characterized by this property. One family of curvature lines is made up of segments of circles or straight lines. And in particular, if you have a conformally flat hypersurface in R4 with three distinct principal curvatures, one of which is 0, it must be one of the hypersurfaces in the previous examples of types A or B. A cylinder over a surface of constant Gauss curvature in R3, or a cone over a surface with constant Gauss curvature in F3. And in particular, if this hypersurface is minimal, it must be a cone over a Clifford torus. Well, going back to Cartan, he not only realized that there exist such hypersurfaces, conformally flat hypersurfaces in R4 with three distinct principal curvatures, but he gave us somewhat mysterious characterization of them by the integrability of some complex distribution you can define. I'm not going into that, but only mention that much later, Hertrich Jeromin has used Cartan's results to show that on any conformally flat hypersurface in Euclidean space with three distinct principal curvatures, you can find local principal coordinates, which are of Guichard type. This means that the coordinate lines are tangent to principal directions at any point, and the induced matrix satisfies these conditions. The coefficients are related by this expression. But he did not prove that conformally flat hypersurfaces with three distinct principal curvatures are characterized in this way. And neither gave additional conditions which would imply that the converse is true. What he did was something else. He considered a conformal diffeomorphism of an open subset of the hypersurface onto an open subset of R3. And since the condition of being a Guichard orthogonal system is conformally invariant, he realized that for each conformally flat hypersurface with three distinct principal curvatures, one can associate an orthogonal system of Guichard type. And he was able to show that conversely, you can produce from each orthogonal system of Guichard type in Euclidean space a conformally flat hypersurface. So, in a certain sense, studying conformally flat hypersurfaces with three distinct principal curvatures is equivalent to studying orthogonal coordinate systems in R3 of Guichard type. But it's not quite easy to construct a conformally flat hypersurface from an orthogonal system of Guichard type, and conversely. And what he did in a series of papers that followed his result was to try to classify orthogonal coordinate systems in R3, satisfying some additional conditions, and then to understand which conformally flat hypersurfaces are associated to them. So we try to obtain an improvement of his result by characterizing which additional conditions you must impose on a orthogonal system of Guichat type to imply that it is conformally flat. And to state this more precisely, I need to recall the notion of a holonomic hypersurface. So we call a hypersurface holonomic if it carries global orthogonal coordinates, which are principal. This means that the coordinate vector fields are eigenvectors of the shape operators. The coordinate curves are principal, are lines of curvature of the hypersurface, in other words. Once you have a holonomic hypersurface, well, let me mention that any surface is holonomic, of course, but this is a strong restriction in higher dimensions. It's in fact equivalent to requiring that for each eigendistribution of the hypersurface, its orthogonal complement be integrable as a distribution. Well, once you have a holonomic hypersurface, it's convenient to define those two sets of functions. These functions Vj's are just the length of the coordinate vectors. And these functions capital Vj's, which are the principal curvatures multiplied by the lengths of the coordinate vectors. And in terms of these functions, the Gauss and Codazzi equations of the hypersurface become very, well, before that, in terms of those functions, the first and second fundamental forms of the hypersurface can be written down in this way. It's usual to call this pair the associated pair of the hypersurface. And in terms of them, one has this way of expressing the Gaussian Codazzi equations of the hypersurface. And then when one can show that, of course, from the fundamental theorem of hypersurface, that once you have a solution of this system of linear, nonlinear PDEs, you can produce a holonomic hypersurface having those functions as associated pair. Well, what we have been able to prove was that if you have a holonomic hypersurface whose associated pair satisfies not only that condition that appears in Geromin's result relating those functions Vi's, but also those two further relations between them and the functions capital Vi's, which are the coefficients of the second fundamental forms, then the manifold is conformally flat. And the hypersurface has these three distinct principal curvatures. So this result states that conformally flat hypersurfaces with three distinct principal curvatures are precisely holonomic hypersurface whose associated pair satisfy those three relations. Of course, one can express those relations in a cleaner way by introducing this Lorentzian inner product. So those relations just say that this vector is a light vector at any point. It's orthogonal to this other vector, and this one in turn is a unit space-like vector. Yet another way of expressing the same thing is by saying that, one has a holonomic hypersurface whose associated pair satisfy besides the condition that appears in Jerome's result, those three additional ones which express the coefficients of the second fundamental forms in terms of the coefficients of the first one and the mean curvature function of the hypersurface. So, one first application of this characterization of conformally flat hypersurfaces with three distinct principal curvatures was to develop a Hibokku transformation for this class. I will not go into many details on the Hibokku transformation. I will just mention the process that one can obtain from it to generate a family of new examples of such hypersurfaces starting from a given one. And it goes as follows. You start with a holonomic hypersurface whose associated pair satisfies those conditions. This means a conformally flat hypersurface with three distinct principal curvatures. Then one has this linear system of PDEs involving 9 unknown functions. This function, here we have 3 functions. Here 3 more functions, so those give 9 unknown functions. But it's a linear system of PDEs, and once you have a solution of this system, it always has these 2 first integrals. And if you choose initial conditions so that the 2 constant that appears on the right-hand sides vanish, and also impose that this new function omega vanishes at that point, then you can construct a new conformally flat hypersurface with 3 distinct curvatures given explicitly in terms of the first one and the solutions of that system. So, in this way, you obtain a process to generate a new family of hypersurfaces starting from a given one. And a nice feature of this transformation is that you can apply it even for trivial solutions of the Gaussian-Codazzi equations that determine such a hypersurface. And if you do that, you start with a trivial solution, you can obtain explicitly parameterized ones. Well, from now on, I will report on some results that in which we have specialized the condition and consider hypersurfaces which have, in addition, constant mean curvature. This was in part motivated by a result by Defebvre, who proved that such hypersurfaces do not exist if the mean curvature is non-zero in Euclidean space. So we felt it was a good test for our previous result, at least if you could give a simpler proof of his theorem. And in fact, we could generalize it for any ambient space form, not only Euclidean space. So there does not exist any conformally flat hypersurface in any space form with 3 distinct principal curvatures and non-zero constant mean curvature. So the natural question to study now would be, what happens in the minimal case? Are there examples of minimal hypersurfaces which are conformally flat and have 3 distinct principal curvatures? Well, at least one example we already know, a cone over a Clifford torus. So it might be a good conjecture whether it's the only example or not. Until now, this is the only example I know. And in fact, this example can be also adapted to any space form by means of the notion of a generalized cone. What I mean by a generalized cone is just a hypersurface that is generated in this way. You start with a surface in an umbilical hypersurface of a space form, and then for each point of the surface, you go along the geodesic of the ambient space that starts at this point and is tangent to the normal of the umbilical hypersurface in the ambient space. Just in the same way you do to generate a cone over a surface in the sphere, in Euclidean space. And it turns out that if you consider a generalized cone over a surface which has constant curvature in any umbilical hypersurface of the ambient space, you get a conformally flat hypersurface, which has three distinct principal curvatures. Well, the one of each is zero, actually. And if you choose this surface to be a Clifford torus in a three-dimensional sphere, you get a minimal conformally flat hypersurface with three distinct principal curvatures. So the example of a cone over a Clifford torus in Euclidean space can be easily extended to any space form. And the question now is, are there any further examples of such hypersurfaces? Minimal conformally flat hypersurfaces with three distinct principal curvatures? And what we could prove first was that except in Euclidean space, you cannot find any further example. The only example of a minimal conformally flat hypersurface with three distinct principal curvatures is a generalized cone over a Clifford torus. Well, how one proves that? Well, you consider that general system of equations given by the Gaussian Kodály equations, add the condition of being minimal, make horrible computations, and finally you get a contradiction when C is not zero. But you can't find a contradiction if C is zero, which leads to the question of, would there be any examples in this case besides the cone over a Clifford torus? And it turns out that the answer in this case is yes. And we have been able to determine exactly how many of them do exist. And then form a one-parameter family of examples. I will try to be more precise about this statement. There exists precisely a one-parameter family of minimal isometric immersions of simply connected conformally flat Riemannian manifolds with three distinct principal curvatures. Let me try to give an idea of how one gets such a result, and at the same time I will be more precise about what I mean by a one-parameter family. So, assume you have a holonomic hypersurface whose associated pair satisfies this condition and this one. Recall that those conditions together just mean that we have a conformally flat hypersurface with three distinct principal curvatures, which is minimal. Now it's convenient to introduce new unknown functions alpha I by those relations. And then let us call phi these vector functions, which involves these three coefficients of the first fundamental forms and those three new functions alpha I. What happens is that the Gauss and Kodály equations turn out to be equivalent to this total system of equations for those 6 functions. Well, here I have omitted those expressions which are too big to fit into these slides. So I had to write them down in another slide. Here they are. But besides those differential equations, those functions also satisfy this algebraic one. Well, it's not clear that there do exist solutions of this system of nonlinear differential equations satisfying two algebraic relations. This one and this one. But if you have such a solution, it determines, in fact, a minimal conformally flat hypersurface with 3 distinct principal curvatures, just by means of the fundamental theorems of submanifolds. So the question is now, is this theorem empty or not? Are there solutions satisfying those conditions? So to answer that problem, we try to reformulate the way the solution is given. We have defined those 2 functions. This function f is just inspired by this expression. And have defined this 4-dimensional manifold, which is the set of zeros of those functions. But we have imposed those conditions because in a hypersurface, the functions v1, v2, and v3 must be positive. It turns out that this manifold contains a pair of straight lines, of half lines, which are given by these expressions. And this turns out to be the singular set of this manifold. If you take them out, you get a regular submanifold of R6. Now you define on this 4-dimensional submanifold of R6 3 vector fields. Well, in principle, they are functions from M4 to R6. But it turns out that they are tangent to M4 at any point. Well, the functions A1, A2, A3 that appear here are given by those horrible expressions. And one can prove that those vector fields are everywhere linearly independent in the complement of those straight lines. The straight lines are the set of singularities of x1 and x3. And they are everywhere tangent to the manifold you obtain by removing those lines. And you can show that the Lie brackets of those vector fields are everywhere 0. Well, this is an auxiliary result. Just for this statement, I will give after that. On that manifold, you have those involutions given by these expressions, which preserve the distribution generated by the vector fields x1, x2, and x3. So what I mean by the statement that there exists precisely a one-parameter family of minimal conformally flat hypersurfaces with three distinct principal curvatures is that one have this correspondence between congruence classes of minimal isometric immersions with three distinct principal curvatures of simply connected conformally flat remaining manifolds and leaves of this one codimensional distribution spanned by those three vector fields I defined previously. And this correspondence goes as follows. To each leaf of this distribution, you can associate a minimal immersion which has three distinct principal curvatures of a certain simply connected open subset of Euclidean space, and such that the induced metric is conformally flat. And you also have a local diffeomorphism of that open subset into a leaf of the distribution. The singular set just corresponds to the example that was known previously, a cone over a Clifford torus. Two distinct leaves give rise to non-congruent hypersurfaces, or more precisely, distinct leaves give rise to congruent hypersurfaces only if the leaves differ by one of those involutions of the underlying manifold I described before. And once you have a minimal conformally flat hypersurface, either it's an open subset of a cone over a Clifford torus, or it's congruent to the hypersurface you construct from a leaf of the distribution I mentioned before. Well, so far we have only been able to show that minimal conformally flat hypersurfaces with three distinct principal curvatures do exist besides the cone over a Clifford torus, and to describe the moduli space of such hypersurface, how many of them exist. But we haven't been able to say much about their geometry or even to construct an explicit example. I hope I have attracted the attention of the interest of some of you to solve one of those problems. Thank you.